Our next speaker we're about to hear is Dr. Jesper Schramm, and as a remarkably well qualified technical engineer, mechanical engineer, professor at the Technical University of Denmark, it struck me that I might reflect on Steve Jobs a little bit and the visionaries that he inspired. I recall a statement that Walter Jacobson made about Steve Jobs, that vision without execution is merely hallucination. And I'm just saying that because I'm sure today we're not going to have any hallucinations, so we're just going to hear the real thing. Professor?
Yeah, thank you for inviting me here today. I'm honored that if I look at the topic here, it seems to be very huge, and I'm honored that you thought I could speak about this all by myself and in 20 minutes. Looking at this slide, you will notice that at my university we speak a language that no one else understands. This logo is, of course, to give you an impression of that we are very good at mathematics, but I'll keep the presentation free of mathematics. Being one of the last speakers here, there's a good chance that many of your points has been put forward already, and I think Leslie Bromberg took a part of my presentation, and Martin Tournier took another part, and Sebastian took the last part. Anyway, I hope I have a few points left that has not been put forward so far. I have chosen to take a big overview of the stuff, looking at the basic characteristics associated with application of methanol, and from that picture I will try to give you my best view of what is needed in the future in order to progress with methanol application in combustion engines. So this is what I'm going to talk about today, starting by fuel properties. And here you have something that you probably can't read, but it's the fuel characteristics of ethanol in the first row or column, then gasoline, diesel, and methanol in the last column here. Concentrate on the red spots because that's the characteristics that I'm going to talk about. We see from the octane number and the cetane number, as we well aware of, that we are dealing with an obvious spark ignition engine fuel, since it has a high octane number and a low cetane number. So what kind of engine-related advantages does this lead to? Yeah, we can increase the compression ratio, as has been said many times before, with the high octane number. And we have an effect of what we call charge cooling, because heat of vaporization of methanol is high, so we start the compression with a very low temperature and pressure, and this means that we don't have to use as much work in the engine compressing the charge. And also this shows the laminar flame speed of different fuels, alcohols and gasoline, as a function of fuel-air ratio. And we can see that methanol is excellent in this context. It has a very high engine flame speed, and meaning that we can run, as Sebastian said, the engine very lean and still have a decent flame progress. So we have an increased efficiency using methanol compared to gasoline, because we can operate leaner, we can increase the compression ratio, and we have this effect of charge cooling. So we have actually higher power based due to the high efficiency, and this again can be used for downsizing as an extra benefit. So this is the well-known work from Brewster at the Environmental Protection Agency of US, and you can see if you increase the methanol content from 50% to 100% in gasoline, we obtain high efficiency. So theory and practice come together in this case. What you can also see is that we actually have a broader operation range. We can operate the engine more flexible because it's not as dependent on the load situation. Of course, there are also some disadvantages, and since we have a very low calorific value of the fuel compared to gasoline, the fuel system in some cases needs to be increased. The capacity needs to be increased, and maybe sometimes we cannot use the same fuel system as for gasoline. We have, as we know, cold start problems because of the high heat of evaporization. And we also have some problems with evaporative emissions. And then there are some issues concerning miscibility of methanol or alcohols in general with gasoline and diesel. Now, this is the vapor pressure of different fuels. And we can see that actually the vapor pressure of pure methanol is lower than gasoline. But something strange happens if we mix it with gasoline, then actually the resulting evaporative pressure exceeds the evaporative pressure of gasoline. So therefore we need a higher capacity of canisters and things like that to reduce evaporative emissions. So that's a drawback of the fuel. This is a kind of diagram for the state of mixtures of water, gasoline, and ethanol. As you know from ethanol, it cannot be produced without chemical treatment free of water. So there's a chance that if you get below the curves here at different temperatures, water, ethanol, and gasoline will separate in 3 phases. And since water is the heaviest one, water will gather in the bottom of the tank, so you'll have pure water in the engine, which is of course a showstopper. In Brazil, they sell hydrous ethanol, 7% water it contains. And if they were to mix this with pure gasoline, they would have trouble, because then there would be possibilities to have mixtures in the fuel tank along this line here. And there would be a problem with separation down here. But that is why they don't sell pure gasoline in Brazil. They sell something which is called gasohol, containing 22% ethanol. So they will not interfere with the separation. This is not the same situation with methanol, which is actually not containing any water from production, or almost any. But during storage and transportation and so on, we should be careful because it is hygroscopic, so it can absorb water actually. So this might be a topic to be careful about in the future. And with methanol, it's the separation trend is even worse than with ethanol. Looking at compression ignition engines, we have these different options. We can use methanol with ignition improvers, expensive stuff that promotes the compression ignition. And we can use methanol in dual fuel solutions with diesel fuels. We can use diesel methanol blends, and we can use other blends. This is what I'm going to talk about. Now, this is something you haven't been presented to earlier. In my work at the IEA, Implementing Agreement for Advanced Motor Fuels, we put up a collaboration project between Scania in Sweden, VTT in Finland, and my university, DTU in Denmark. And in VTT, they actually tried different ethanol fuels. We have been in the market. There has been an additive, an ignition improver for ethanol available for many years, and now a lot of new and cheaper additives are popping up on the market. So we took some of these additives, where additive 1 is a commercial one that has been known to work very well for many years, and then two new additives, additive 2 and 3, put it into ethanol and also methanol in the end. So you will see that fuel 1 to 5 is ethanol plus different additives and different water content. But fuel 6 is actually a combination of ethanol and methanol and the additive, and fuel 7 is pure methanol with the additive and zero water content. This is a Scania truck engine, production engine, with a very high compression ratio of 28:1. So the conclusions from this investigation of methanol, ethanol, and additives combination in the Scania engine was that the fuel 7, which was the methanol and additive fuel, was running a bit roughly on low load. And the injection times were clearly longer, of course, with methanol, because you need to put in more fuel in order to get the same power out of the engine. But we didn't see any difference in emissions and cylinder pressure data between the additives, and we didn't see any bigger differences due to the water content of the fuel. But we did see with the methanol fuel the most significant changes in emissions on the bad side, I'm afraid. And this, of course, is most likely due to the extended need of injection times. And this only tells me that for methanol application in diesel engines, in some cases, we need a new fuel system in order to be able to operate on methanol, a fuel system with a higher fuel capacity. Yeah, but those were the basic conclusions from that study. And you can see here the different fuels on the influence on energy consumption. There were basically no influence on energy consumption from the different fuels. These experiments took place at VTT in Finland, and in my university we investigated the same fuels. And this is the heat release rate from the different fuels. The red one on the, this is called fuel 0. The red one in the most right one in the picture is pure ethanol. And then we have the 3 fuels with different additives. And from this figure we do see different heat release patterns, meaning, of course, that we have to change injection timing when we use different additives. But this can be solved, of course. We did see approximately the same efficiency as you saw from the figure before at Scania as well. We can also use, make ethanol ignite by compression ignition. This might be more difficult for methanol because it has a high heat of vaporization, but we cannot do that without heat addition to the intake air. So we needed to heat up the intake air to 80 degrees centigrade in order to make ethanol self-ignite. Yeah, if we consider dual fuel solutions, we may have indirect injection or direct injection of methanol together with direct injection of diesel. That is what's seen generally. We need, this is a good solution because we need less engine modifications, and this needs an explanation because it should be compared to something, and this is in relation to converting a diesel engine to a spark ignition engine. Then this is a much better solution, and also compared to conversion of diesel engine to natural gas engine, it's easier with a liquid fuel like methanol. It's a rather unexplored concept, even though we have seen a very brilliant solution from from Wärtsilä today on the Stena line. We generally see that fuel consumption and particulate emissions is reduced, but with NOx emissions, it is my general opinion that results are inconclusive. Some say higher NOx emissions, and some investigations say lower emissions. So we need a kind of, or we could go for a kind of optimization in the future, and this is the stuff that Martin presented earlier, because in one end we have a pure homogeneous charge compression ignition, which is a perfectly premixed charge of fuel and air, and in the other end we have pure diesel combustion, and they are not the perfect way of doing it, as Lund has shown already. In the HCCI end we have a very high heat loss, and therefore the efficiency of the engine is not perfect. In the other end, the conversion of fuel energy to work on the piston is not the optimum way of doing it from a thermodynamic way. So we have loss of efficiency in that end. But the right way of doing it would be somewhere in between, where we have an optimum efficiency. And that is something that I think needs to be explored a little further in the future for methanol, because, for instance, combinations of methanol and DME could control this way of combustion, or controlling the combustion process through what we call RCCI, reactivity control compression ignition, and also different combinations of fuel could be brilliant for investigating this that we call partially premixed compression ignition. So this is a way to improve the combustion principle in the future if we explore that a little more. We also have diesel methanol blends opportunities where we mix the fuels directly before it is applied to the engine, and 15% is normally considered as possible, even though we have seen higher concentrations of methanol blended in diesel. We see that particulate emissions decrease in these cases, and other emissions, to my best knowledge, is not conclusive in any way. This is well suited for older engines in order to reduce particulate emissions from engines that cannot be converted in other ways. And then I've seen a lot of other combination of fuels. Methanol, gasoline, the green ones are applied in spark ignition engines, the black ones in diesel engines. There are many possibilities. If we turn to emissions, very general, yes. Gasoline engine application, we generally see a reduction of carbon dioxide and fuel consumptions, and hydrocarbon emissions and carbon monoxide emissions. But NOx, again, is very inconclusive. We need smart solutions to that. I think maybe Sebastian is one of those guys who knows how to do this. But if you look through the literature, you won't see any clear picture of NOx emissions. Diesel applications, we could generally see reduction of carbon dioxide and fuel consumption if we apply methanol in this solution. And we also see reduction of particulate matter. NOx, again, is very inconclusive. However, we should also remember that reduced emissions is today not an argument in itself. Some people actually claim that cars are in many areas cleaning the air because the exhaust is cleaner than the intake air. And that is not a joke. And that, of course, doesn't hold for carbon dioxide, but in other cases it does. And this, of course, is not true for Volkswagen. And this is a joke, but not really, because yeah, we know that Volkswagen, they were cheating, but it seems as a general trend that other companies also have difficulties fulfilling NOx regulations. So
all companies are following the legislation, but the problem is the legislation on the heavy-duty side. We have a more advanced legislation that makes things better.
Yeah. Okay, yeah. Anyway, there are some opportunities there to apply methanol in the right way, because there are some obvious theoretical indicators showing that we can reduce NOx emissions with methanol. So, longer term perspectives, that was the whole idea about my presentation here. On road vehicle perspectives, we must move from flex fuel vehicles to dedicated methanol engines and cars. And we may use what we call gem fuels as a transition state to get experience with the right technology. If we consider diesel engine dual fuels, we have these opportunities to optimize efficiency through partially premixed compression ignition or reactivity compression ignition. There are many theoretical ways of doing this, and in practice this seems to work as well as they have showed at Lund. And there are new ignition improvers on the market. That's another perspective that should be investigated in the future. Electricity, I think rail, we have electricity competition, so that's probably not going to be an attractive market for methanol. But marine certainly is attractive, as we've seen many times today. And for aviation, of course, it's not an idea because of the low calorific value. The plane will not be able to lift with all that methanol in the tank. And yeah, a transition state dedicated engine would be these gem fuels, because we can investigate the effect of increased compression ratio, turbocharging, and downsizing, of course. Yeah. We have many combinations of fuel, as I mentioned, and we can apply them in different ways, different fuel systems. One thing that I met was this DIAB, direct injection alcohol boosted engine, which is basically a gasoline engine, and when you kind of pressure the engine to high load, then you can, through a separate methanol system, for instance, you can inject a small amount of methanol in order to lower the temperature and thereby the knocking. And this would lead you to be able to increase the turbocharging rate and the compression ratio. So a fundamental understanding on the combustion processes, thermodynamics, and related to the way the fuel system and the engine operates is, to my opinion, very important to progress with methanol application, because there are some opportunities in methanol. So this is essential, as I see, in the long term, being able to predict what's going on with the combustion process and the thermodynamics processes when we apply methanol in different combustion principles. And being able to predict fuel economy and particularly NOx formation, because there are some opportunities there for methanol application. That's what I wanted to say.